part of our chapter deals with reactions that are known as oxidation and reduction reactions. This is probably a brand new topic to most students listening to this lesson. Redox reactions, that's the short word for putting together oxidation and reduction. They're commonly called redox. This is a very common type of chemical change where it's an umbrella of many other recognizable patterns. A redox reaction could also be a type of combination reaction. It could also represent a decomposition reaction. It could fall with a single replacement reaction, and even the combustion pattern. So the last series of reactions with Lesson 2 and Lesson 3 were all double replacement reactions. We started with formation of a precipitate. We did the acid-base neutralization, making a water, and the last little bit there was all about gas formation, the three different driving forces of a double replacement. Now notice the next category called redox. I've listed all the other recognizable change, combinations, decompositions, single replacements, and combustion patterns all fall under this big umbrella known as a redox reaction. What do all of these four different patterns of chemical change have in common? Well, it all has to do with the transfer of an electron through the course of the chemical change. Ionic compounds are formed through the transfer of electrons. An oxidation-reduction reaction involves transferring electrons as reactants move to products. When we think about a transfer of electrons, what we're going to end up looking at is who changed their charge from the left to the right side of arrows. Change of charge. What changed the charge as reactants form products? And that will help us identify what was oxidized and what was reduced. Oxidation and reduction talk about a transfer of electrons. Now, just to remember ourselves, we talked about the Bronsted-Lowry theory of acids and bases, and we talked about that as being proton transfer, and the term conjugate pairs was set up with acid-base chemistry. This is just a side note. Conjugate pairs with acids and bases deal with proton transfer. Opposite of that, when we're transferring of electrons, tracking negative transfer, negative electrons, we're going to look at some redox. So as a step one, before we can write any type of chemical equation that involves transferring electrons, we have to learn what are oxidation states. How do we go about assigning charges so that we can keep track of what's changed? Somebody became more positive as they lost electrons, and somebody must become more negative as they gained electrons. So we're going to begin this lesson by learning how to assign oxidation numbers. It's a simple bookkeeping method. It's not necessarily true of what we find in nature, but it works. So it's a bookkeeping method that we've organized as chemists to come up with a way of assigning these charges, these oxidation numbers, so we can track electron flow. So just a way of keeping track. We need to memorize the rules for assigning oxidation states. So let's begin top of page 11 in our notes, going through these rules one by one. Read them with me carefully, and we're going to make some side notes for each one. Rule 1 reads, the oxidation state of elements in their elemental form, the way we find them in nature in other words, is always 0. The elemental form of an element is 0. So, for instance, in nature, I would find sodium solid. Sodium solid would have an oxidation state of 0. Hydrogen is one of those lucky 7 diatomics. It is going to be oxidation state of 0. So any element written, an element is a symbol written by itself, not carrying a charge, gets assigned a 0. Keep in mind there are 7 naturally occurring diatomic molecules who also have an elemental form oxidation state of 0. Number 2, oxidation states for monoatomic ions are the same as their charge. Monoatomic, a single atom carrying a charge. So up here I said, here's sodium atom, oxidation state of 0. What if I had a sodium ion, oxidation state of +1? Ions only exist in aqueous solutions, so I automatically know these are aqueous. Hydrogen ion has an oxidation state of +1. Molecular hydrogen, oxidation state of 0. Hydrogen ion, oxidation state of +1. Chloride ion, oxidation state of -1, and so forth. So the oxidation state for the ions, as we find them on the periodic table and deduce their charge, match their oxidation number. Rule number 3. Oxygen is assigned an oxidation state of -2 in its covalent compounds, except as a peroxide. Then it is assigned a -1. Now this rule is extremely important. Let's take some time with it. Rule 3. Oxygen, we know when it forms an ion, is O-2. I'm going to tell you 99% of the time oxygen's oxidation number is -2. We have this rare exception, and it's worth noting because I see it appear on the AP exam almost yearly. The exception is if we have a peroxide. This is known as oxide ion. What is a peroxide ion? Well, it gives us an example, Na2O2, sodium peroxide. Here we have barium, was it barium? Let me peek up again. Nope, it was hydrogen peroxide, H2O2. Now I know sodium's a +1, oxide must be a -1, but there's 2 units of it here. So this is just a little bit weird, isn't it? The overall charge here is -2, and that's why we come down and bring that 2. So the peroxide ion is O2, -2. So if I deduce that, give it to the lowest whole number ratio, the overall charge is -1. The peroxide, this is confusing, so I'm really going to try to stress this. This is peroxide. The ion is O2. It overall carries a -2, doesn't it? Because 2 units of a -1 give me an overall charge of -2. -1, 2 of them there, gives me a -2. Since barium's a +2, the compound barium peroxide, BaO2. The compound barium oxide, BaO. So please make yourself a note. This is a rare exception. Peroxides, you're going to notice that it just looks odd to you. Why don't we reduce this down? Well, peroxide itself is O2 carrying a -2 charge. So therefore the single atom of oxygen in a peroxide carries a -1 overall. Rule 3, so important. 99% of the time oxygen is a -2. Once in a great blue moon, we have a peroxide, sodium peroxide, hydrogen peroxide, barium peroxide, and so forth. Rule 4. Hydrogen is always assigned a +1 when bonded to a nonmetal and a -1 when bonded to metals. Another critical rule. Memorize. Let's discuss it to help it kind of sink in. So rule 4, here was rule 3. Let's talk about hydrogen. Oops, rule 4 is what I meant to write. It says if hydrogen is written in the first position, bonded to a non-metal, HCl, I'll do H2S, just based on charge, +1, -1, +1, -2. If I have hydrogen written in the first position, bonded to a nonmetal that carries a negative charge, hydrogen is a +1. This is called the hydrogen ion. Now the flip side of that rule says, What if hydrogen's written in the second position, hooked to a metal? Let's suppose I have NaH. This guy here is now carrying a -1 charge. This ion we learned is hydride. NaH, hydride. How about CaH2, calcium hydride? The charge on hydrogen written in the last position when hooked to a metal is -1. Hydrogen in the first position hooked to a non-metal carries a +1 charge. Rule 4 is reminding us that hydrogen can be a +1 or hydrogen can be a -1, simply depending on the substance it's hooked to. Rule 5, pretty straightforward, no exceptions at all. Fluorine, always a -1. The most electronegative element on our periodic table, always a -1. Fluoride, -1. Now remember, molecular fluorine, the way we find it in nature, 0. Rule number 1 review. Rule number 5 says if it's hooked in a compound, it's a -1 charge. Rule number 6. The sum of all oxidation numbers in a neutral compound is always 0. We've learned that when we try to crisscross charges, we make an electrically neutral compound. The sum of oxidation numbers in a polyatomic ion equals the charge on that ion. So for instance, let's suppose I have a neutral compound, NaCl, sodium chloride. The number of positives electrically balance the number of negatives to give us 0. Suppose I had a polyatomic ion, I'll just make up chlorate, ClO3, -1. The sum of the two oxidation states, one would come from chlorine, one would come from oxygen, their sum would give me -1 overall. By the way, what would the oxidation number of chlorine be? Rule number 3, oxygen is always assigned a -2. Always, always, unless it's a peroxide, and this is not. So the total negative 3 units here, 3 times -2, the total negative is -6. What must the oxidation number on the chlorine be so that when I sum the two numbers together, I get a -1? What, when added to -6, brings me to -1? Well, it's a +5, isn't it? The oxidation state on chlorine in this polyatomic ion called chlorate is +5. Now, chloride, Cl-, a monoatomic ion, its oxidation number is -1. My goodness, it changes depending on what it's involved with. Chlorine in this polyatomic ion is a +5. Chlorine in this binary ionic compound is a -1. That takes some practice, doesn't it? Let's assign oxidation states to each of the elements in the following, practicing the rules as we go through. Here we have carbon dioxide, CO2. What rule number might play a role here? Well, let's read. Rule number 3 about oxygen. I always start with the oxygen because there's a rule about it. It says oxygen is always assigned a -2. Oxygen is a -2 oxidation number. The total negative then is -4. Rule number 6 says when I sum these oxidation states together for a neutral compound, it ends up to be 0. So what must the oxidation number of carbon end up being so that when I add it to a -4, I land at 0 on the number line? Well, you've got it. Carbon must be a +4. A +4 when added to a -4 is a 0. Starting with the oxygen, we deduce the carbon from it. Let's try another. Here we have nitrate. Oh, maybe I'll just extend the page. That's probably easier. nitrate. NO3, -1. So here's an oxygen. We know that this is not a peroxide, so it's always assigned a -2. Oxidation state of oxygen is -2. 3 units of a -2, 3 times 2 gives me a total of -6. Now remember, this is a polyatomic ion, so the sum of the oxidation states will land at a -1. What must the oxidation number for the nitrogen be so that when I sum with a -6, I go to a -1 on the number line? A +5. The oxidation number of nitrogen in the polyatomic ion nitrate is a -1. How about H2SO4? Well, rule number 3, I like this one. It gives me an idea about oxygen. So oxygen is always assigned a -2. 4 units of a -2 give me a total of -8. This is a neutral compound, so I know that when I'm done, I got to add to 0. Here's hydrogen written in the first position. Rule 4, when hydrogen is bonded to nonmetals, it carries a +1. 2 units of that +1 give me a total of +2. What's the missing number that will be the oxidation state for sulfur? Well, we're going to need a +6. 2 units here, +6 gets me a total of +8. -8 lands me to 0. The oxidation number of hydrogen, +1. The oxidation state of sulfur, +6. The oxidation state of oxygen is -2. How about this one? Fe2O3. Well, the rule for oxygen, -2. 3 units of a -2 give me a -6. I know it will end to be 0 because it's a neutral compound. I know that the total positive has to be +6. To get me to 0, the total positive is +6. But notice I have 2 units of the positive ion. 6 divided by 2 gives me a +3. Iron's oxidation state is +3. Oxygen's oxidation number is -2. And friends, the last one is an error. Fe3O4 would produce a fraction. Could you just please cross that off? It doesn't work. Alrighty. After we cross that off, we have a you try it. What noble gas element has the same number of electrons as the fluoride ion? Well, the noble gas, of course, helium, neon, argon, krypton, xenon. So it's group 8A. Noble gases is the last column in our periodic table. If fluoride ion is F-1, find it on the periodic table, you'll notice that fluorine, element number 9, gains an electron. What noble gas does it become? It's right next door to neon, the end of row 2 on our periodic table. What is the oxidations number of that species? Well, neon oxidation number is an element in its natural state. Rule number 1, we know that it would not carry a charge at all. Fluoride has the same number of electrons as neon. Fluoride gained an electron, carries a -1 charge. Neon, a noble gas, would never gain or lose. Its elemental form gives us an oxidation number of 0. So important to practice assigning oxidation numbers. Let's try some more. First one we have is hydrogen sulfide. Hydrogen sulfide. Chemical formula is H2S. Rule number 2 at the top of our paper, oxidation number for hydrogen. It's rule number 4 dealing with hydrogen. Hydrogen is assigned a +1. So that gives me a total positive +2, making sulfur here a -2. Sulfur in hydrogen sulfide is a -2. Elemental sulfur, S8. This is commonly called flowers of sulfur. Well, here's the big key word right here, elemental sulfur. The way we find sulfur in nature, it's assigned a 0. Any element found in its natural state has an oxidation number of 0. Sulfur dichloride. Sulfur dichloride. Hear those prefixes? This is a molecular compound, isn't it? Knowing that sulfur dichloride is molecular, let's begin with chloride. Knowing where it lives on the periodic table is telling us it's a -1 charge. So the total negative here, 2 units of that -1 give me a -2 overall. So sulfur here must be a +2. First scenario, a -2, then a 0, now a +2. It's changing all over the place. Remember, this is just a way of bookkeeping. It's not anything to do but just bookkeeping. Sodium sulfite. Na2SO3, sodium sulfite. Oxygen rule, -2. 3 times -2 gives me -6 overall, coming from oxygen. Sodium in the first position we know to be a +1. 2 units of that give me a +2 overall. Always leave this middle one to figure it out last. What must be in this position to land at 0? Oh yeah, it's got to be a +4. Oxidation state of sulfur here is +4. And we have one more in our set, the sulfate ion. Sulfate is a polyatomic ion, SO4 -2. The oxygen rule tells us oxygen's a -2, so the total negative is at -8. Polyatomic will sum to give me their overall charge, so that's a -2 overall. What must I add to a -8 to end at a -2? A +6. Sulfur in the last example is a +6. Sulfur gave us an example of an element that changes drastically just depending on the type of compound it's found in. The first of our problems is asking us to assign oxidation numbers to atoms in the molecules and ions. Determining the oxidation number for the indicated element in each of the following. For example, with number 1, the carbon in the polyatomic ion called oxalate, C2O4-2. Looking at our rules for oxidation, rule number 3 had suggested, and I'm just going to write larger so we can see that clearly, C2O4-2. It says that we know oxygen is always a -2, except if it's in a peroxide, which this is not. It's a polyatomic ion known as oxalate. You can find it on your polyatomic chart. If oxygen's assigned a -2, the net negative coming from the oxygen, its total contribution is a -8. Rule 6 from our oxidation numbers would show us that polyatomic ions will add indeed to their charge a -2 in this case. That shows us that the net positive charge would have to be a 6. A +6 and a -8 adds to a -2. 2 units of the carbon, 6 divided by 2, each would have to be contributing a +3. Carbon in the oxalate polyatomic ion is a +3 charge. Number 2, As and As4, the arsenic. This happens to be the way this atom is found in its natural state, As4. Rule number 1 from our oxidation rules would show any element in its natural state is assigned a 0. Number 3 says, let's find O in K2O2. K2O2 is indeed a rule breaker for the oxygen rule. Oxygen is always a -2 unless it's in a peroxide form, as it is in this example. This is a compound, potassium peroxide. Potassium we know to be a +1. Its total charge would be a +2. Knowing that the total negative would have to be a -2. -2 divided by 2 gives this oxygen a -1 overall charge. Potassium peroxide, the oxygen is a -1. In the next compound, NaH, sodium hydride. This goes to Rule 4 for assigning oxidation numbers. Hydrogen is assigned a +1 when hooked to nonmetals, and it's assigned a -1 when hooked to a metal. In this case, sodium, carrying a +1 charge, makes hydrogen a -1 charge. The hydride ion is a -1. Number 5. Here's a polyatomic ion called sulfate. SO4 carrying a -2 charge. The polyatomic ion sulfate. Well, we know oxygen to be a -2, so the total contribution from the oxygen is a -8. Polyatomic ions will add to the charge assigned to them, which in this case is a -2. Therefore, we can see the total positive must be a +6. Sulfur is a +6 in sulfate. The last example, another polyatomic ion called phosphate, PO4 -3. On our polyatomic ion chart, PO4 -3 is named phosphate. We know oxygen to be a -2, giving a total contribution from the oxygens to add to a -8. Overall, it must be a -3. So therefore, the positive charge, a +5. A +5 and a -8 land me at a -3. So a +5 is the oxidation state of phosphorus in phosphate. We're going to start working some examples of reactions that fall under this big umbrella called redox reactions. Remembering that what they all have in common, all these kinds of reactions, be it a combination reaction, could be a decomposition, could be a single replacement, and it could be a combustion pattern, not the double replacement. All of these 4 patterns fall under this large umbrella called a redox reaction. And what that commonality is between them is how they change charge. When reactants form products, we'll see that there have been a change in their oxidation state as reactants go to product. Now let's take an example of a combination pattern first. So a familiar pattern of a combination. Suppose we have a metal, Na for sodium, and it would be in a solid state, reacting with the elemental form of chlorine, Cl2, it's a molecular element, and it is in nature in the gaseous form. The pattern of chemical change for a combination reminds us that when a metal, such as sodium, combines with a nonmetal, such as chlorine, they're going to form an ionic compound and they're going to hook by charge. We had studied this very much in depth in our first year chemistry. They form a compound, an ionic compound, commonly called a salt, sodium chloride. Sodium with its plus charge, chloride with its minus, we get NaCl. Now remember, when we studied the 6 rules for assigning oxidation states, any element in its natural form, such as sodium, has an oxidation state of a 0. Chlorine, found in its elemental form as a molecule, has an oxidation state of 0. Now when they hook together, notice now how they're carrying a charge. The oxidation number of sodium is +1, and the oxidation number of chloride is -1. Sodium changed charge. It started as a 0 and became more positive. Chlorine went from a 0 and became more negative. We've had a transfer of electrons. Now let's go ahead and balance this. We'll need a 2 in front of each of these. So 2 NAs plus Cl2 makes 2 NaCls. You'll need to adjust that coefficient in your notepad page. So we've had a transfer of electrons. When sodium became more positive, let's show this. Sodium started at 0, became more positive. Now what has happened is it's lost 1 electron. Notice how a +1 charge when added to the negative charge of an electron, gives me the 0. So the charges on both sides of our arrow are matching. They're both at 0. When chlorine started at 0 and went over to chloride, -1, well, it had 2 units of -1, we're going to see a total of 2 electrons being lost there. And you can see why we distributed the coefficient of 2 in front of each of the sodium, so that the number of electrons lost equals the number of electrons gained. We're going to practice this half reaction method multiple times. What we've just done is split the oxidation and reduction into 2 halves, the half reactions. We can label this process as oxidation and this process as reduction. The oxidation is a loss of an electron. Reduction is the gain of an electron. In this combination pattern, we saw sodium and the chlorine change charge, and they did so through the process of transferring an electron. Let's take a peek at a second pattern that's very familiar to us, called a combustion pattern. When a hydrocarbon combusts, our pattern of chemical change, let's take an example of a simple hydrocarbon called methane, CH4. Adding oxygen and a whole bunch of heat and light are produced along with carbon dioxide and water. Here is the skeleton of our combustion pattern. Let's go ahead and take a minute to balance. 4 H's, I think we'll need to double the water. 2 and 2, we'll need to double the oxygen. So here's our balanced combustion pattern. Now how might this also be labeled as a redox reaction? What has changed charge? Well, let's take a minute and use those 6 rules to identify what are the oxidation numbers of each of the elements. Here's an element in its natural state, molecular oxygen. Any element found in its natural state is assigned a 0. Over here, hydrogen, this is rule 4, I believe, hydrogen is attached to a non-metal, making it a +1. Carbon would have to be a total of a net 4 to sum to equal 0. 4 units of a +1 balance a -4. How about on this side? Oxygen's always a -2 unless it's a peroxide, but it is not here in this carbon dioxide molecule, giving me a total of -4. So carbon must be a +4. Hydrogen's +1, -2. So what has changed? Well, right away I noticed that oxygen started at a 0 and became more negative. It has gained electrons, becoming more negative by taking in more negative electrons. Carbon on the number line went from -4 all the way to +4. When you become more positive, you've lost electrons. Of course, the hydrogen did not change, and oxygen could have gone to either place. I could have gone either way, and so had it changed from 0 to -2. So with our very first exposure to redox reactions, we looked at a combination pattern and we looked at a combustion pattern. Both of these have a larger umbrella called a redox reaction that describes any type of reaction where charges or oxidation numbers change on an element from the left to the right-hand side are now going to be called combustion. So oxidation, that term oxidation, means an increase in the oxidation state, an increase, becoming more positive on the number line. You do that by losing those negative electrons. Take away a negative particle and the resulting species is more positive. The term reduction means to reduce your oxidation number. You become more negative, and you do that by gaining those negative electrons. There's a little saying that helps me remember oxidation and reduction. Some teachers I've heard use the term oil rig. Oxidation is loss, reduction is gain. However, the one that I've always used is Leo and Gur. There's a funny little sentence. Leo the lion says Gur. Leo, loss of electrons, is oxidation. Loss of electrons is oxidation. And Gur, the gain of electrons, is reduction. Something that is oxidized has increased its oxidation number on the number line by becoming more positive. Something that is reduced has gained electrons and becomes more negative on the number line. Now, just to make this a little bit confusing, and I apologize for doing this, but we've got some vocabulary associated with this, and it is confusing at first, but kids will eventually kick it in. We have the term agent to describe. So let's go ahead and fill in the blank. Oxidation means an increase in oxidation state. Reduction means a decrease in oxidation state. But up here where it says, and I'll go ahead and show the slide, the substance that is oxidized is called the reducing agent, and the substance that is reduced is called the oxidizing agent. Go ahead and fill those blanks in, and then let's go down and kind of give some clarification to those vocabulary words. Remember in our previous example where we had sodium atom losing an electron, and we wrote this out as an oxidation half reaction, a loss of an electron. Because sodium is being oxidized, it is called the reducing agent. The term agent means it's forcing the other reactant to become reduced. We had chlorine gaining 2 electrons. Let me add that back in correctly. Gaining 2 electrons to form 2 units of chloride. Notice the charge on both sides of our arrow are the same. They don't have to be a 0, but they have to be the same. -2 is the charge on the left, and -2 is the net charge on the right. This was called a reduction half reaction. The gain of electrons is called reduction. But however, chlorine is now going to be called the oxidizing agent. Chlorine forced sodium to be oxidized. Sodium forced chlorine to be reduced. So it's really just a matter of flipping the word when you add the word agent. If you're asked to find the reducing agent, really it's another way of asking you, what was oxidized? If you're asked to find the oxidizing agent, it's just another way to ask you, what was reduced? Very important. I would put this a little highlighted note in your notepad page, the term agent. Very important to process the term agent and then the vocabulary associated with it. Agents force the other reactant to do the opposite of what it has done. Wherever we've had an oxidation, we must have a reduction. Reducing agent is the substance that was oxidized. Oxidizing agents is the substance that was reduced. By the way, a good another note, agents are always reactants. Let's go on and take a peek at the next slide. The term agents, and I'm just processing this a little bit more. Oxidizing agent gets reduced. It gains electrons. More negative oxidation state. By gaining electrons, you're being reduced. Reducing agents gets oxidized. You lose electrons and become more positive. An easy way to remember that, Leo the lion says grr. Losing electrons is oxidation. Gaining electrons is reduction. Oxidation becomes more positive. To be reduced becomes more negative on the number line. Traditionally, this term agent gets confusing for beginning students, but as I said, just with a little practice, it becomes quite easy. Let's identify the oxidizing agent, reducing agent, the substance that were oxidized, and the substance that were reduced. And we'll just use these following examples, and these are typed out in your notepad page as well. So let me kind of come down and we'll write these out one at a time. Here I have elemental form of iron, FeS, with the elemental form of oxygen, O2 gas. And it's a combination pattern forming an ionic compound, Fe2O3. I'm going to take a minute to balance this. There we go. Now I know from first year chemistry this is called a combination pattern, but now under this larger umbrella it will also be defined as a redox reaction. Always begin by identifying the initial states of their oxidation numbers. The elemental form of any atom is 0. Iron, oxidation of 0. Here's the elemental form of oxygen, assigned as 0. Oxygen is a -2. Iron becomes a +3 if I simply just uncrisscross this ionic compound. So here I've had iron go from a 0 to a +3, and oxygen went from a 0 to a -2. Iron became more positive, didn't it? The loss of electrons is oxidation. Oxygen became more negative. The gaining of electrons is reduced. Remember the term oxidation, what was oxidized, what was reduced? What are the agents? Always come from the reactant side. Iron was oxidized, and therefore it is the reducing agent. And can I just write RA and we'll get that clear? Reducing agent. Molecular oxygen was reduced, and therefore it is the oxidizing agent. Shall we try another? Here we have Fe2O3, iron 3 oxide, that's in solid form, reacting with gaseous carbon monoxide, and it forms liquid iron and 3 carbon dioxide units in a gaseous form. Did I miss the coefficient? I sure did, right there. A 1:3:2:3 stoichiometric ratio. We're being asked what's oxidized, what's reduced, and then to identify the agents. So step 1, we better figure out what the initial oxidation numbers are. We just worked this guy. Oxygen's always a -2. I uncrisscross here. Iron's a +3. If oxygen is a -2, carbon must be a +2. Elemental form of iron, here's 0. Oxygen's always a -2, gives me a total of -4. So now the carbon has gone to +4. Stand back and look. What's changed in the charges? I notice iron went from a +3 to a 0. It's going down on the number line. It is getting reduced. Grr, gaining electrons, making it become more negative. Carbon started at +2 and went to a +4. That's becoming more positive. Losing electrons is oxidation, making the element become more positive. So identify what was oxidized and what was reduced. The reactant of Fe2O3 is the oxidizing agent because iron was reduced. And I'll just use that symbol. The second reactant, gaseous CO, is the reducing agent because carbon was oxidized. Give you a moment to process that. We started this journey by just simply assigning oxidation states. With one becoming more negative, there must be going the opposite direction. Carbon became more positive. We have to have one of each. Notice how I grabbed the entire reactant to identify the agent. It's not just iron, it's iron oxide that's the oxidizing agent. It's not just carbon, but it's carbon monoxide that's a reducing agent. I take the entire reactant's formula to identify the agent, and then in that I describe what the element was that changed charge. Here's that last example. In this one I have a little adjustment to make. Could you please make sulfite the polyatomic ion, but it actually carries a -2 charge. In my notepad page I only have it listed there as a -1. Please make that adjustment. We're going to have that with a hydrogen ion, which is a +1. A permanganate ion, which is MnO4 -1, polyatomic ion. Make the same adjustment here. Here's sulfate, but it carries a -2 charge off our polyatomic. We have a water and then a manganese +2. Alrighty, what's change charge? Well, let's start by assigning all oxidation numbers, and these should go pretty fast the more we practice. Starting with the oxygen here, I know it's a -2, so therefore the net negative is -6. It's a polyatomic ion carrying a -2 overall. We made that adjustment there in the notepad. So sulfur must be a +4. Here's a monoatomic ion, so it matches the charge of +1. Oxygen is a -2. There's 4 of them. So manganese here must be starting at a +7. Let's do the product side. Oxygen is always a -2, so I'm now at a total of -8. Sulfur must be a +6. Here's an easy one, +1 -2. And a monoatomic ion matches the charge, so manganese now to +2. What's changed? Here, sulfur was a +4. It increased on the number line to a +6. It was oxidized. Losing electrons make you become more positive. Here's the manganese. Started at a +7, went to a +2. It was reduced. There's the GR part of our half reaction. Gaining electrons is reduction. So let's identify. Sulfite, SO3 -2, because it was oxidized, is the reducing agent because sulfur was oxidized. The permanganate ion, MnO4 -1, is the oxidizing agent because the manganese was reduced.